Okay, so it is my pleasure to introduce Adam Epstein from Warwick University. And his talk is titled Newhouse Phenomenon in Transcendental Dynamics.
So hi, this is actually the first time I've given a online talk to a conference. Although I guess it's much like giving a lecture to my students. But anyhow, it's a pleasure to be here in Barcelona, whatever that means, and hopefully we'll all be able to do it for real at some point soon. So what I have to speak about today is some work with Lhasa from a few years ago at this point, which is, I think, cute and germane in a few ways. The title here is very catchy. The title here is totally Lhasa's contribution here, A Newhouse Phenomenon in Transcendental Dynamics. So it means I get to talk a little bit about what a Newhouse, or what the Newhouse phenomenon, the classical Newhouse phenomenon is, which is something that occurs in 2 and higher dimensional dynamics, which is typically seen as by contrast to 1-dimensional dynamics. But in fact, in transcendental dynamics, we have an instance of that too. So I should say what that is. But to set the context for it, let me review some extremely basic and classical facts. So all of this is about the iteration of entire functions from the complex plane to itself. And anything of interest will be for transcendental entire functions. So that's just all a given throughout. Okay, and then there's the usual basic classification of periodic cycles according to their multipliers, attracting and different or repelling. In the special case of multiplier 0, super attracting. Okay, and then the facts of life are as follows. So any polynomial has only finitely many attractors. That goes back to Fatou. That's already over a century old. And then the sharp version of it is it goes back to Duody Hubbard. That polynomial of degree d has at most d minus 1. So I guess I'm counting here attractors rather than non-repelling cycles, but let's just say attractors here. Okay, so the Duody Hubbard refinement, as is well known, sharpens a heuristic argument of Fatou. There's perturbations involved, and to get to be able to do perturbations with enough care to get the sharp result involved quasi-conformal mapping. So once that observation was made, this result was proved. Of course, there's a more general version due to Shishikura for rational maps. Okay, by contrast, the transcendental entire function can have infinitely many attractors. It's easy to make examples, just write them down. So z minus sine z, for example. I mean, even in fact, you can. I mean, it's even easier than writing them down. I mean, in fact, the way I like to think about this is to not start on the complex plane, but to start on C star, right? And then write down the simplest map there that has say 1 super attractor, and then lift it, which is basically how you get this example. Okay, so. So such a map having infinitely many attractors cannot be of finite type, or class S as it's called. It's an extension of this Fatou-Shishikura principle that I guess that's Eremenko-Lubitsch in this case. Okay, but of course here the set of singular values for this function z minus sine z, of course, has to be periodic by construction. So it certainly isn't a finite set of singular values. It's not even a bounded set. Okay, so that basically sets the context for the question, or it will when I get to the slide. I guess I got ahead of myself here. Okay, so so more just review of notation, just so that it's clear when the theorem is stated. Okay, so for an entire function f, we can consider the set of its critical points. Okay, so there you're thinking of the z is in the domain. This is where the derivative is 0. And then there's the set of critical values, the set of images of those critical points. Okay, so the set of critical values, this is well known to be what you look at first when you study the dynamics of polynomials or rational maps, but it's also well known that when you pass to the transcendental setting, you should also look at the asymptotic values. Okay, so again, because it's an entire function, so infinity is that it comes for free, and we're going to look at the set of finite asymptotic values. So limits along paths tending to infinity. And well, it's either a definition or it's a lemma. I prefer seeing it as a lemma, that the set of all singular values is the closure of the union of those. Right. So I like to take the definition of singular values as well, to take the definition of non-singular values, say regular value, as a value in the range, which possesses a neighborhood which is evenly covered. So which is such that the preimage of that neighborhood consists of a collection of copies that all project down homeomorphically. So in the sense of covering space theory. And then it's a 1 or 2 line argument that in fact the set of singular, in high generality, the set of singular values is the closure of this union. And it just somehow makes it easier to proceed that way rather than define it that way when you start talking about compositions. And it's a little advertisement. And then finally, just as a comment here, we'll also talk about what I'll call them the set of, well, it's not quite the set of omitted values. It's a little more, I'll call them the set of Picard exceptional values, although that way will mean something else in some other context. So this will be the set of all finite values which are attained only finitely often. And the point is that by Picard's theorem, there's at most one of those. Right, so I mean, it could be like 0, which is omitted completely, which is taken never by the exponential function, but maybe it could be the value 0 for z times the exponential function, which is taken once, for example. So it'll be at most one such value. Okay, and then finally, catching up to what I think I was stating before. All right, so I'll say that function from C to C is a finite type if the set of singular values is finite, right? So of course, if the closure of a set is finite, then the set is finite, right? So you see, that's sort of built into the definition the way I gave it, that little observation somehow. All right, and then correspondingly, we'll say that it's bounded type if the set of singular values is bounded. This is known at this point as the Eremenko-Lubitsch class. Okay, so it's easy observation that both of these conditions are preserved under composition, hence under iteration. So it makes perfectly good conceptual sense to sit down to try to prove theorems for all finite type maps or all bounded type maps. Okay, and then here's the result of Eremenko-Lubitsch that I stated before, which is just the I'll call it the Fatou Hubbard-Shishikura result. In this context, a finite type transcendental map has only finitely many attractors, and in fact, there's a sharp upper bound, which is the number of singular values. Okay, the quantity which has to be finite by definition of finite type, and that in fact is also the bound on the number of attractors. Okay, so what this means, so if going back, of course we did have this example, z minus sine z with infinitely many super attractors, but in hindsight, it means that the set of singular values, it's not surprising that it's infinite. In fact, it's more than infinite, it's periodic, it is not bounded. Okay. So, in some sense, this begs the question, or maybe not this, but okay, maybe it's just now is a historical point, right? So there was a time, which at this point is, well over maybe let's say 2 decades ago, where I think it was a matter of some discussion and thought. Could somebody actually produce results or properties that actually drove a wedge between finite type and bounded type? Something exhibits something for a bounded type that could not happen for a bounded type map, but somehow finite type map that exhibited for a bounded type map. And up to some point, all of the theorems about the one or about the other. I mean, that's sort of a tautology, but the relevant part is that up to that point was within the careers of many of us. Okay, and then there were and then of course this was chipped away. Now, so the result I'll talk about here is one such, but I think it's relevant to say that that particular significance has been overshadowed by many results of Chris Bishop in his school, specifically in terms of wandering domains. So at this point, I don't think anyone would doubt that there should be significant differences between what you could say and prove about finite type, what you could say about bounded type. Okay, so this result here is one little piece of that discussion. Okay, so my recollection, which grows rather hazy, is that this question was formally raised, to me, the first time by Helena Mihalevich Brandt, probably at some workshop in Denmark somewhere. But okay, so all right, here are the results, and then I'll give a little bit of the story of mine and Lasse's working it out, and then just present the construction. Okay, so the theorem, or the slogan, say, is there is just a bounded type entire map with infinitely many attractors. Okay, so it's an existence theorem. Of course, you take a look at a statement like that, and presumably, if you can prove that, you can. I mean, however you're proving that, you can probably prove more. It's just it's a question of what you feel like cashing out of your construction, how much work you want to put in. It's a matter of craft, perhaps. Right. So, and it's also a matter of judgment, how much craft to put into it. So, this is all part of the history of this. All right. So, okay. So, in fact, bounded type entire maps with infinitely many attractors are prevalent in suitable families. And I believe that that's actually a technically correct usage of the word prevalent in literature where people study smooth, say finite dimensional families of in smooth dynamics in several variables. There's a notion called prevalence, which is some combination of full measure or some positive measure and topologically large, but I forget which. But in any event, okay. So here's a formal statement, a much sharper version, which could be used in applications if one could foresee applications of this. Okay, but this sort of condenses it all down. This is a theorem here about one parameter families. So I want to emphasize this formulation, or even the very possibility of this sort of a formulation, where all of the power is really packed into some statement about not just one parameter families, but the most trivial of one parameter families, starting with some map, maybe a cleverly constructed map, and then just looking at translations of that map. Right, so the family is trivial. Maybe this sort of puts all the work or hides all the work into producing an appropriate map to start with. But it's a good way of packaging the work involved. Okay, so the statement is: let F be an entire map with the following properties, such that the interior of the closure of its critical value set contains a repelling fixed point. Interior of the closure, the critical value set. How might you arrange that? Well, for example, if the critical value set, for example, is dense in the unit disk, right? And all you have to do is arrange that there's some repelling fixed point in the unit disk. Okay, so then there exists a neighborhood of zero and a residual subset R. This is in the sense of bare category. Right, the intersection of canonically many open dense sets, so it's topologically thick. Right, in other words, it's something like the irrationals, the Gaussian irrationals as opposed to the Gaussian rationals. Right, there exists a neighborhood of zero and a residual subset R, such that for any beta in that residual subset, in that small neighborhood of zero, the map F plus beta has infinitely many attractors. Right. So not only can you find some map as infinitely many attractors, but a reasonably generic or I don't know, I don't know if generic's the right word, whatever. It is presumably not so hard, or not so much to expect of rational maps for transcendental maps and infinite dimensional families, that you might find maps like this, and then the rest of the talk is basically showing how. Okay, and showing how, in fact, it's not hard at all. Okay, so I'm not going to actually give the details of the proof of the theorem, but the ideas are all contained in the next 2 slides, and it's a well-known idea. So just some more definitions. This set, this is the dynamically exceptional set. Maybe this is Fatou exceptional or something, right? The set of all points in C with finite backward orbit. Okay, we always want to exclude those from, or pay attention, beware of those in various discussions and claims. That's E of F. Okay, fortunately, that's a small set. It's at most 1 point. In fact, it's a subset of that set P of F, which was defined in the non-dynamical way before. So this is sort of a priori even smaller, again by Picard's theorem. Picard's theorem applied to a couple of iterates. And then the backward orbit of any other point accumulates everywhere in the joint set. All right, so everything's just like polynomials. Okay, and then here is the precise statement of the, here it's called a proposition, but it's really a lemma, right? The basic construction that's used to produce attractors, right? I mean, there's a claim about attractors. The attractors have to come somewhere. Where is the proposition where they come from? It's here. Okay, so making this, rough conceptual analogy to higher dimensional dynamics, which I do not do. Okay, right. But maybe I should go back and say historically a little bit more. So, I mean, way back in the mists of time, like 60 years ago or so, when Smale and others were founding modern smooth dynamical systems, and they observed, or they put early interest on hyperbolic systems. So here you want to think that you're on, say, some smooth manifold, which is compact, or maybe have some other finiteness condition, right? So, I mean, R2 or C2 is not compact, but maybe you pin things down to infinity in some way, or you just work on a compact manifold, right? And then this definition of hyperbolicity involved there being finitely many attractors. Okay, the question was, and this is things are defined, right? This is an open condition, no matter what dimension you're in. And the question, or the hope, or the conjecture, and it was incredibly naive, was that, well, maybe this should be not only open but also dense. I guess it was conjectured because, I mean, in the even earlier when people were studying circle maps, right? There's the Kupka-Smale, Kupka-Smale, Moore-Smale, whatever. There is some statement like this that is true for circle maps if you say it that way. It's sort of never circle homeomorphisms. But anyhow, so there's hope. The hope that this set could be dense was shot out of the water almost immediately in the early 60s by Sheldon Newhouse, who basically, I mean, get the first formulation of this principle about there being under suitable conditions, there was always a residual set in parameter space where you had such phenomena and then other phenomena. And there the mechanism was homoclinic bifurcations. Okay, homoclinic bifurcations in several dimensions, where this involving a stable and an unstable manifold. Okay, so you need at least 2 dimensions for that to even have that picture which I've not drawn here. But anyone working in 2 dimensions knows this. And that's one of the things that makes 2-dimensional dynamics, whether real or complex, so much richer than 1-dimensional dynamics. Okay, so we clearly don't have this here. We're just doing 1-dimensional dynamics. Okay, but we can get around that. I mean, there's this homoclinic argument, which does get used elsewhere in 1-dimensional homomorphic dynamics. If you just want to produce periodic points of some type or another, there's a little game you can play. Anyway, so here's this proposition, okay, with that preamble. Okay, so take an analytic family of entire maps parameterized by a connected open neighborhood in 0 in the complex plane. And what else do we give ourselves? We give ourselves parameterized, well, we give ourselves two functions. We assume we also have functions chi lambda and zeta lambda, where chi lambda is it's an analytic family of repelling fixed points of the corresponding maps. Okay, so that sort of that definitely comes for free, because if you have to start with a repelling fixed point, then any perturbation will have one. You can just solve for that. Then the other is you should have a function zeta of lambda, such that the function zeta of lambda minus f lambda of chi lambda, in other words, vanishes at 0, but not identically. Yeah. Okay. And then finally, chi of 0 should not be one of these dynamically exceptional values. Okay. And the conclusion is, for any sufficiently large positive integer p, there exists a parameter such that the point chi sub mu has period p under f sub mu. Okay. This is the sort of thing where it's probably better to show a picture than state all of this, but I don't have the picture, and at this point I wouldn't know how to import it properly. But that's the proposition. Okay. Now the question is the execution of it. Okay, so this is the meaty slide. This has a lot packed into it here. Because, well, I mean, this is all about a construction at this point. Okay, so let me talk about this rather slowly. In fact, let me check my time and see how, so no, this is okay. Okay, so here we start out with an entire map with a repelling fixed point. Okay, right. I mean, again, the role of repelling here in all of this is contained in this picture where, I mean, the point is, if you have a point which maps, if you have a point which is close to a repelling fixed point, right, then when you iterate, you'll map outwards for some time. And at some point, you might map so far outwards that you might hit a pre-image of that repelling point, and therefore nearby pre-images of nearby points, for example, yourself. Okay, that's the heuristic in that of that proposition, right? So there's a use of Montel's theorem in there, I should say. I mean, probably anyone can reconstruct it at this point from that. Okay, so we know we're gonna be starting with an entire map with a repelling fixed point. Well, that's not particularly difficult to arrange. You basically take any entire map and post-compose it with an affine transformation, and you can get, so that's no problem. Okay, so start with that, and now, so take a neighborhood. Okay, so suppose that you have some, suppose that you now have a neighborhood of that repelling fixed point. Okay, and now here, this assumption here is actually meaty. Okay, so I want this to be what I call an isolating neighborhood. So a disk such that whose closure contains at most one singular value in the sense of the previous slides. And if there is such a singular value, that it should be this repelling fixed point zeta itself. Okay, so right, so in particular, zeta is either a regular value or an isolated singular value. Okay, so that's not something that just any entire map will have. But for example, if you have an entire map of finite type, right, then this is easy, right? Because any point has a neighborhood such that the closure, whose closure contains at most one singular value. That will actually be the point. I mean, it's at the very end when we sit down to make everything to quote unquote write down an example, we're going to try to choose the simplest or most congenial entire map possible with these properties. Okay, so but for now, take an entire map with repelling fixed point, take an isolating neighborhood for that fixed point. Okay, and now look at the set of all connected components of the pre-image of that neighborhood. Okay, so what are these components going to look like? Okay, so from the hypothesis, we know that, first of all, if zeta is not a singular value, then all of these pre-image components will just be homeomorphic copies. The restriction of F to any of those pre-image components will just map homeomorphically down to D. But zeta could be a singular value. Okay, in which case we should delete that value and any pre-image it might have in the domain. All right, so what are the possibilities? So what you're left with is either the restriction of F to one of those deleted components will either be a finite degree map from a punctured disk to a punctured disk, or it'll be an infinite degree map from a tract to a punctured disk. Okay, so I guess I haven't defined it here, but it's maybe implicit, little d sub v. So if you consider the set of all connected components of the pre-image, that's some countable set. Some of those components are bounded; those are the finite degree ones, and some are unbounded; those are the tracts. Right, the bounded ones have a d sub this d sub v is finite. It's a net positive, it's positive integer, and the tracts, for the tracts, this d sub v is infinite. Okay, so now let's just consider this as a set now, right? So it's some countable set. Now I'm saying consider the set Gothic B, Fraktur B, of all functions, right? So these are really sequences. Right, but I've written it this way somehow. So, right, so this is a sequence space. So all functions from this countable set of components to the unit disk, and whose image is bounded in the unit disk. Okay, I guess what I mean by that is such that the supremum over the sequence is less than 1. Well, whatever. I mean, if D is the unit disk, I'd say the set of all sequences whose image is compactly contained is contained in some compact subdisk. Okay, and then the observation is that this is an open neighborhood of the origin in appropriate finite space. It's just the L infinity space on that countable index set. Okay, so analytically, this is about as soft as things could be. Okay, and the claim is that now there exists an analytic family. Okay, so analytic family defined where? So defined on this open neighborhood of the origin in this infinite dimensional Banach space. This is an infinite dimensional analytic family parameterized by a small ball in a Banach space, in an L infinity Banach space. And what are the properties that we're claiming here? Okay, so in fact, some of the notation here should be reminiscent from Kirill's talk that's the other day. Right, so of course we want these to be, I mean, the title here is Deformations, right? So this family is meant to be a quote natural deformation space of F. Now I don't have an axiomatic characterization of what a natural deformation space is. Maybe I'd like there to be one. Maybe that's what Lasse and I still need to formulate. I don't remember, right? But certainly these are all the desired properties you'd want to read off of it. Okay, so what are they? Okay, so the family should be F sub B, and it should depend analytically on this boldface B in this ball in the L infinity space, and we like something a little bit funny about the note. I think this should be a phi. Yeah, this is somehow not quite correct. So I have phi sub B composed with phi, F sub B composed with phi inverse agree. Okay, so there should be some statement about what this psi sub B is, and it doesn't seem to be on this page. Okay, but by reference to Carol's talk, right, this is going to be some map which is close to the identity. Okay, I don't know why I say agree. Oh no, okay, yeah, it's some map which is close to the identity and which is going to be obtained by solving an appropriate Beltrami equation. I'll just leave it that way. Such that, and the covering properties of the maps in this family are as close as possible to what you started with, except for the fact that we've made this perturbation here. Okay, so the point is that the map globally, F sub B is globally essentially F, except when you're in one of these regions, one of these preimage regions over D, you imagine first mapping as you would, and then just perturbing a little bit to move that critical value over to wherever you like. So, I mean, basically imagine some quasi-conformal deformation in D, in the range. And then for each preimage that you have, make this perturbation separately, right? So you do it in each component. So you may have had lots of critical values, lots of critical points mapping to this repelling point originally, but after perturbation, now you have them all mapping near, but possibly to different points. Okay, that's the claim of this theorem, is that you can do that. In fact, you can do it with enough control that I mean, I guess this is what I was sort of saying heuristically. You can keep control so that the set of critical points remains what you think it is. The set of critical values remains what you think it becomes what you think what you wanted it to be. That nothing whatsoever happens. You can arrange nothing whatsoever happens regarding the asymptotic values. They're just not really coming up in this construction. They don't have to. And again, about these Picard exceptional values that only have finitely many preimages, they also just don't come up in this construction. They're not seen, or we don't pay attention to them. Okay, so the proof of this is entirely quasi-conformal deformations. You draw the picture, you look at the disk in the range. You see clearly with quasi-conformal maps how to perturb the range. You can move this disk, moving that critical value anywhere you like, and say being the identity outside that disk. And you make corresponding deformations in the domain that are compatible, so that the resulting map composed with these two quasi-conformal maps is now entire again by the measurable Riemann mapping theorem. That's what this statement here is that we've done that. Okay. So now, I mean, to try to make this as concrete as possible, I mean, I'm never going to give you an actual formula for such a function, right? I mean, I think we had to talk about how difficult it was to give a formula for a map with a Hermann ring of period greater than 1. So, I mean, why are these things hard? Because it's not like you can just like give yourself some finite number of algebraic conditions just to sort of reach out and solve for and follow. Right. So, but what I can do is sort of sharpen the claim to sort of show how prevalent such functions are. All right. So let me put some constraints on this. Let me tie a few hands behind my back here. So let's get an example that has finite order. Example of a map with infinitely many. Oh, okay. Let me go back a little bit. Right. So now I should have said something here. Right. So this is the result of the construction. Okay, and then once I've made this construction, we'll observe that, well, in particular, right? So in particular now, since the set of critical values, let's just say, assume there's no asymptotic values here. Then the set of critical values is essentially just the set of all values prescribed in the sequence, set of all entries in the sequence. So the coordinates of B are the critical values. So it's very easy to make them dense. Just arrange for them to be just take an enumeration of the Gaussian rational points in the unit disk, for example, and assign those values, or assign the values in the disk of half that radius, I suppose, with any enumeration you like. right? And then the corresponding map in this family will have the property that the closure of the set of singular values contains a repelling period, a repelling fixed point, right? Okay, at least if you look close enough to zero, right? Because you do want that point to remain repelling. Okay, so this together, so that observation, you make this construction, okay, and then you can just read off the result from Lasse's formulation here, right? I mean, you don't need this formulation. By the time you get this formulation, you could have, with slightly more work, using that lemma, using that proposition I mentioned, but sort of doing some bookkeeping in infinite dimensions. You could sort of by hand do a perturbation and get a new super attractor, and then make a small perturbation so that remains attracting, but get a new super attractor, and do all of this by hand and grind out infinitely many cycles, infinitely many attractors, right? But I think the cleverness, the beauty of it is the statement here is it puts all the work into something more non-dynamical, right? It's just playing around with the critical value set, the sort of preparatory step, and then anything with dynamics is contained in this one parameter family statement here. Okay, so let me conclude here by making this a little bit more precise or sharp. Okay, so yeah, let's give ourselves some constraints. Let's find a finite order example. Here's the definition of order that everybody here knows. All right, so, and let's make the order as small as possible. All right, well, we know that the smallest we're going to be able to get is order 1/2. This is well known. This theorem was mentioned in a talk yesterday. It's the theorem of Wiemann. This is well over 100 years old. One of my favorite results. It puts this constraint for maps with bounded singular value. It's about geometry of tracts, right? So we're not going to do any better than order 1/2. Okay, I'm just reading off various properties here. The Alfor's distortion theorem, just as a name check here, right? I mean, so just by assuming finite order already puts strong constraints that can be useful in dynamics. Okay, now, all right. So the heart of this is a quasi-conformal deformation argument. Well, so that's fine, but of course, if I want to actually prescribe the order of an example, maybe I can't actually give an explicit example, maybe I could at least prescribe the order of an example. Okay, well, what I have to work with is the order of the function I start with, right? So maybe if I want to get lowest order possible, I should start with a function of order 1/2, a class S function of order 1/2. Here's one, a finite type map of order 1/2, something in the cosine root z family, sine pi over root 2 root z, and then square that. All right, so this particular normalization, reason for this particular normalization is I've put the repelling fixed point at 0. There's this multiplier that's pretty obviously repelling. Okay, but whatever I start with, whatever order it has, who knows what order I'm going to end up with after I do these quasi-conformal deformations, right? So if you want to say something about that, you need to be a little bit more careful, right? So, I mean, if you look at the definition, right, and of order, it's pretty clear that when you do this deformation, you're pre and post composing. Actually, it turns out that only one of those compositions is relevant. But leaving that aside, there's a composition involved with a quasi-conformal map, and quasi-conformal maps are they're Holder, but they're typically not Lipschitz. Okay, so the fact that they're Holder means that you should expect, actually you're entitled to expect that the order has changed. Might change it only a little bit, right? But it's, I mean, because you're sort of looking at it's well, whatever, because the order is like looking at exponential z to the m, but Holder means you could affect that power. So if you want to keep the order as it was, you have to be more careful. All right. So the killer app for this was mentioned in Kirill's talk yesterday. This is the Alfors. No, not Alfors. There were several names. Some of the with Teichmüller, Wittig, Belinsky, maybe Lecto, maybe Jenkins. Heaven knows, maybe other people with whatever refinements. This result, I think in Lecto's book, it's called, quote, conformality at a point, or asymptotic conformality at a point, right? So here, here, the statement is here. All right, so, I mean, area property is a name that Lasse and I gave because we wrote, not this paper, but another paper all about this condition here, using that in other interesting cases here. Okay, right, so, but the theorem is the following. So if you have a Beltrami differential mu, so you're working in a neighborhood of zero, say, and you have a Beltrami differential mu such that the integral of mu of z over absolute value of z squared is convergent, then the corresponding quasi-conformal homeomorphism with, or homeomorphisms with, I guess I should say normal, then you, let's say up, then if you then normalized appropriately, the corresponding solution of the Beltrami equation has the property that phi of z minus z over z is little minus 1 is little o of 1. I'll state it that way. That's the way it was stated and used the other day. So there's no actual Beltrami differential appearing here. What you're seeing, what's appearing here, you should think of the Beltrami differential as something like as some constant t times the characteristic function of the support. In any event, okay. So under that assumption, if you have a function with that property, if it has the area property, then any of the functions in this corresponding family will have the same order. The order will be constant in that family. Okay, that's what the Teichmüller, Belinsky, Wittig, Lecto, Jenkins theorem gives you in this. And this other comment here, this is not used in the construction, but it's just sort of completeness here, right? It's, I mean, it's a weaker, I mean, so not every function has the area property, right? So as I said, there's a paper that Lasse and I have about functions with the area property and how that relates to the question of rigidity of order. I think it's actually some, well, whatever, this way, that paper was motivated by some basic examples, and somehow in that paper we never got around to sorting out the basic example. We kind of both realized that after the paper was published. So if anyone's interested in something which should be in the literature and might be fun to work out, they should contact me about this, about showing that basically maps for Schwarzian derivative have the area property. Okay, but in any event, this map certainly has the area, but that's an exercise by hand, so you can verify very easily that this integral here is finite. Okay, if you don't assume the area property, then there's some much weaker and much less interesting statement, but it's just here for completeness, that if the sequence decays suitably, if the perturbation is suitably mild, then you won't be changing the area, then you won't be changing the order either. But I don't think that that's anywhere near strong enough to get the consequences we wanted out of this. Okay, so to close, I guess I've already shown this now, but this is about as explicit as it's going to get, where you say start with this function, square of sine pi over 2z, right? Why this function? This is, I would say, in some sense, for me, the simplest entire function is probably the exponential, but it's not the lowest order the finite order could be. Okay, so this one here, right, it's normalized nicely. The recurring fixed point's at 0. It's got multiplier pi squared over 4. The critical points are at the positive integers. And they're all simple. And the corresponding critical values are either 1 or 0, depending on parity. So again, pretty much simple as possible. And furthermore, preimages of critical values are all critical. In fact, I haven't thought. I'm wondering how many, if enough of these things you would characterize this, but let's leave that aside. There's no asymptotic values. None of this was about asymptotic values at all. It's a map of finite type. Right, we have 2 critical values, no asymptotic values. There are no Picard exceptional values. Right? Every value is attained often. You can solve, right? I mean, this is just, I mean, if you know the logarithm, you can find preimages of this, right? Okay, and finally, the order is 1/2. That's easy. Sine grows like the square of sine grows like the exponential, and then this is composed with square root of z. So it's order 1/2. And the map has the area property, which, okay, I mean, again, I've given that statement here in terms of an integral, but the way you should really think about this, and again, this was stated yesterday in Carol's talk, this is just saying that if you take a small neighborhood of the disk and take its preimage, right? So of course the preimage can only accumulate at infinity. But let's think of the plane now, not with the usual area element, but with the logarithmic area element. So that's what this dx dy over mod z squared is. So think of this as a cylinder, right? You sort of send 0 off to the bottom end of the cylinder, right? And then with that area form, you ask, is the preimage of a small neighborhood finite? Okay, that's the area property. So something like that. If you think of that for the exponential function, that's obvious. You just do the calculation, and a minor modification of that calculation works for this example too. So that's more than I should say about that. In fact, I'm finished. I should have finished already. So thank you.
Okay, thank you.